Jai Hind and welcome to all. Myself Shiwani from Department of Applied Science and Humanities in Ajay Kumar Garg Engineering College. Going to deliver a lecture on third lecture on polymer. And to make these slides, I took the help of same two book, Engineering Chemistry by Jain and Jain and Shashi Chawla, and these sites www.acs.org, so on, and SlideShare. So, in this lecture, I will discuss the structure, properties and application of 6 polymers which are mentioned in AKTU syllabus, and these 6 polymers are classified in elastomers as well as fibers. So, 3 polymers belongs to elastomer and 3 from fibers, and the 6 polymers are in elastomers Buna S, which elastomers means basically rubber, second is Buna N and third is Neoprene, and in fibers nylon 6, I think everybody heard this name, nylon 6,6, and last is PET. There are lots of polymers, but in syllabus these 6 polymers are given. So, we will discuss these 6. Now, first let us take elastomers, and elastomers are also called viscoelasters because these type of polymers have viscosity as well as elasticity. Elastomers are long, thin, and we can say elastic polymer. Elastic polymer means when we apply the force, they can be stretched up to 3-4 times, but when we release the force, they come back to original position. It may be due to absence of some polar group or site for hydrogen bonding or bonding, and when they combine, then basically they do not fit in regular pattern. So, there is a basically weak van der Waals forces, so that they can be stretched. So, we can stretching it may be due to their structure, and structure means weak van der Waals forces, and they have basically cross-link structure, or we can say coil type structure. Before these 6 polymers, before 3 polymers in elastomer, first let us discuss natural rubber. We know that the polymers are of 2 types, natural, synthetic. So, Buna S, Buna N and Neoprene, all 3 are synthetic polymer, but the basic unit of rubber is this structure, this butadiene structure, and the natural rubber is isoprene. Isoprene means at number 2 position there is a CH3 group. So, natural rubber is a high molecular weight hydrocarbon polymer, and if we check the general formula, the total number of carbon are 5 and hydrogen are 6. So, C5H8 N or X, and it is obtained by latex of rubber tree, and when latex is removed, then tapping process is done. Tapping means the removal of another thin layer of bark, and rubber tree is Hevea brasiliensis. So, it is this. Now, what is the structure of this? When we draw the structure of rubber, we should remember this point, that the basic unit or the linkage or the chain which provide the cross linking is butadiene. Butadiene means CH2 double bond CH, single bond CH, double bond CH2. So, this butadiene linkage, it provide cross linking, and at number 2 position, if hydrogen is replaced by CH3, it is called isoprene. If hydrogen is replaced by Cl, then it is called chloroprene. And this natural rubber, this occur in cis form as well as in trans form. In trans form, the cross linking, or we can say the fitting of chain is comparatively less regular pattern than trans form. So, we can say cis form means more irregularity, that is it is a natural rubber. Natural rubber means the the fitting of chain is not in exact manner, but in trans form, trans means the pattern or fitting is regular. So, it is basically more hard rubber, and gutta percha is the example of this. Now, processing by cutting the bark of tree, or solution, colloidal solution is obtained, and in colloidal solution the rubber is only present in 25 to 40%, 45%, and the remaining part are water, protein or resinous material. Then this latex are coagulated by acetic acid and then made it into the sheets, and then these sheets are cured under mild heat and for further processing. So, the simple is natural rubber. Natural rubber means polymer of isoprene or polyisoprene. Now, vulcanization. Vulcanization is basically modified process. Natural rubber is useless, or we can say it is like a pure gold, and when we mix copper, then gold is used in a for further use or in ornaments. The same thing, raw rubber is useless, means it has low temperature range, which is about 10 to 60 degree. It is it oxidized by oxidizing agents, by sunlight or by some chemicals. It has stickiness, low tensile strength. So, to make the raw rubber for useful purpose, this vulcanization process has been done. This process is discovered by Charles Goodyear in 1839, and in this process, this is raw rubber isoprene process, and we know that when double bond is present in alternate manner, and then addition always 1,4 take place. 1,4 means addition from this side, then double bond will move here and then this side, that is 1,4 addition will take place. So, it means this butadiene double bond, it comes from this side, this thing, and then chain. Then in vulcanization means the heating of raw rubber with sulfur at 100 to 140 degree centigrade. During vulcanization, the sulfur combine at double bond and it provide the cross linking between the chain. It means initially the raw rubber is like this, but when it is heated with sulfur, then sulfur combined with double bond, and when it combine, then it means the cross linking between the chain occur. And the cross linking during vulcanization, it brings about the stiffening of the rubber by anchoring and consequently preventing the intermolecular movement of rubber springs. And we know that raw rubber, the intermolecular forces are comparatively weak, and but after vulcanization, its tensile strength get also increased. So, what is the structure of vulcanized rubber? The same structure of raw rubber, but at double bond the sulfur will combine. Now, what are the advantage? We know that raw rubber is, it has very limited temperature range, but after vulcanization the temperature range increases. Temperature range increases means it can be used in winters as well as for summers. The tensile strength also increase. Excellent resilience means temperature range, better resistant to moisture, oxidation, some organic solvents, thickness and tackiness it get also changed, and elasticity it become low. And that is why after rubber, if we see our car, then we see that the car can move by the tire, and tire is made from rubber. So, vulcanized rubber it is used for this purpose. Now, application in heavy duty tires, tank linings, reduce the machine vibrations. It is used for material between the two metal surface. Even foam rubber is used for making mattresses, cushions, padding toys, etc. So, this is the just idea of Rohrabar. Now, let us start 6 polymers. So, first polymer is Buna S. Now, what is this Buna S? Bu. Bu means Buna basically. Bu means butadiene. Na means sodium and S means styrene. It means it is a copolymer. Copolymer means 2 type of monomers are there. So, it is a copolymer of butadiene, which provide the basically flexibility, and styrene in a emulsion system at 50 degree centigrade in presence of redox catalyst, which I have taken cumene peroxide. So, butadiene. Butadiene means CH2 double bond CH single bond CH double bond CH2 plus styrene. Styrene means benzene ring with CH double bond CH2, and to make it perfectly the ratio 3:1 is preferred. 3:1 means 75% of butadiene, 25% of styrene, and there is no functional group. It means the addition polymerization that will take place. Addition means when we take N, and since ratio is 3, so we can take 3N and here we can take N. So, when addition take place in butadiene, we know that 1,4 addition will take place. 1,4 means this and this and this, that is the movement of double bond will take place. So, what will be the final structure of Buna N? The final structure of Buna N will be, Buna S will be CH2 single bond CH. Now, double bond it shift between 2 and 3. So, CH sorry double single bond CH2 and then CH, and at CH benzene ring is attached, then CH2 and further linkage N. Now, since 3, so we can write here. So, this is the structure of Buna S, butadiene plus styrene and then addition can take place. So, bond between this and this double bond will provide, and then for further linkage. And it is not necessary that examiner asks directly. If examiner asks a polymer which is formed by copolymerized of butadiene and styrene, and let the 104 gram styrene plus 216 gram butadiene. Suppose examiner asks like this. So, which type of polymer is formed and draw the structure. So, first we see that which monomers are used. Here for copolymerization styrene and butadiene is used, and we know that in combination of butadiene and styrene form Buna S. So, the answer is Buna S will formed. Now, when we draw the structure of Buna S, then we find the moles styrene, and when we take the molecular weight of styrene, it get 104. So, the number of mole of styrene will be 1. Now, when we check the molecular weight of butadiene, it get 54, and when we find the mole, then the moles of butadiene will be 4. It means for this polymerization, examiner took the 4 mole of butadiene copolymerized with 1 mole of styrene, and when we draw the structure of rubber, then it will be CH2, single bond CH, double bond CH, single bond CH2, and then styrene, CH, CH2 and CH, benzene ring is there, this is Buna S, but since 4 moles, so here we write this. Clear? So, if examiner give the moles, then we do like this, but if it examiner asks directly, then we can say generally 3:1 ratio is preferred. It is also known as GRS, that is government rubber styrene, or SBR. SBR is the styrene butadiene rubber, and it is the first synthetic rubber developed during the Second World War by US to overcome the scarcity of the natural rubber. Now, and this is the emulsion polymerization at low temperature minus 18 to 50 degree centigrade, and that is why it is also known as cold rubber. Now, properties: it is a strong and tough rubber, since double bond is there, so it can be vulcanized easily. It is good insulator. It has excellent abrasion resistance. It is resistant to chemical, but swells in oils or attacked by traces of ozone present in atmosphere, and it has very good load bearing capacity, and that is why it is used for making tires. And resilience means temperature range, and because of these properties it is used in manufacturing of tire, in footwear industry, especially for shoe sole, for making wires, cable and insulators, and it is also used for production of floor tiles, tank linings in chemical industries. Now, second polymer, it is again elastomer, same Buna, Bu means butadiene, Na, so in presence of sodium, and N is the acrylonitrile. So, it is a nitrile rubber which is formed by prepared by copolymerization of butadiene. Butadiene is the CH2, CH, single bond CH, double bond CH2 and plus acrylonitrile, and acrylonitrile is CH2 double bond CH single bond Cn. Acrylonitrile, which is the monomer of acrylon paint, acrylon clothes, etc., which is a fiber, but here it is copolymerized with butadiene, and generally 2:1 ratio is preferred. 2:1 ratio means 66 or 67% of butadiene copolymerized with 33% of acrylonitrile. And when we do the polymerization, the same process means no functional group, so nothing will liberate, and when we take N, then direct addition means movement of double bond, so CH2 combination, so double bond will move here, so CH double bond CH single bond CH2. Now, this double bond, it provides the linkage between these two carbon, CH2 CH Cn and up to N. This is a chain of 1000 or 2000 molecules, and to for exact generally 2:1 ratio is preferred. So, we can write 2 here. So, 2. This 2:3 is not necessary, but ideally it is preferred. This acrylonitrile, that is CH2 double bond CHCN, it contained low temperature properties, improves, but high temperature properties it get reduced, like material swelling of material increases and fluid resistance decreases. And this butadiene, it is used to make more elastic and low temperature flexible. Now, properties, it is comparatively more resistant to oil, fuel and other chemicals, it has good tensile strength, as well as good abrasion and compression set resistance, but it is not resistant to solvents. It can be attacked by chemicals, especially organic chemicals, ketones, esters and aldehydes, and it have poor resistance to ozone, sunlight and weathering. The reason behind this, the double bond present in butadiene segment with CN group. Application, it is used in automotive and aeronautical industry because its temperature bearing capacity is comparatively high, which is -40 to 108 degree. It is used to make protective gloves in nuclear industry. It is useful material for disposable in lab cleaning and examination gloves, and Buna and latex is also used for preparation of adhesive, pigments, etc. Now, next is neoprene. Neoprene, I think I have cleared that in butadiene at number 2 position, if hydrogen is replaced by CH3, then it is called isoprene, and if it is replaced by Cl, then it is called chloroprene. So, the monomer of this neoprene is chloropene. Here no copolymerization because one monomer is there, one type of monomer is there. So, it is a type of homopolymer. So, we can say directly polymerization. So, polymerization of this chloroprene, what will happen? This double bond it will go there, and this double bond it provide the linkage. So, we get like this. So, this is the structure of neoprene. This CH2 single bond C, Cl double bond CH, CH2N. So, it is a type of polymer known as polychloroprene and which is produced by polymerization of chloroprene. Now, properties. In this, chlorine is present at the chain. So, it reduces the reactivity of many oxidizing agent, so improves the chemical resistance. Due to low reactivity, it displays good resistance to ozone cracking, heat aging or chemical attack. It also forms a rubber to metal bond. So, we can say it has tendency to harden over time, and it degrades in presence of few common chemicals which are hydrochloric acid, sulfuric acid, etc. Its mechanical properties are comparatively inferior as compared to natural rubber, but it has very good chemical resistance property. It is used for gaskets, chemical jackets, gas line hoses, water resistance products, base resins in adhesive, and the 4 common application is to make laptop sleeves, to make wetsuits, to make small boats and boots. Now, fibers. Fibers means long, thin polymer, but they have very strong bonds between the chains, and that is why they can't be stretched. If you remember the introduction part, when I draw the stress strain chart, then fibers has a strain minimum or lower or 0, while the rubber has stress 0. So, fibers, they are continuous filaments and they are crystalline, present in both plants and animals, and they are used for making clothes, ropes, strings, etc. So, again the fibers are of 2 types, natural fibers as well as synthetic fibers. Natural fibers which are directly obtained, and the cellulose is common example. But we know that when esterification of cellulose, it gives cellulose acetate. Cellulose acetate, and this cellulose acetate is either synthetic or semi-synthetic fiber. Synthetic fibers are nylons, all nylons, esters, acrylon or etc. So, let us take one by one. First is nylon 6. This 6 shows the number of carbon between the one unit. So, in one unit the number of carbon should be 6. Nylon 6, the monomer is caprolactam, and this caprolactam, it has heptaring with 6 carbon atom and 1 nitrogen. This nylon has polyamide series. Polyamide series means NHCO. So, since it is polyamide, so we can say the nitrogen will be present with carbon. It resembles natural polypeptides. So, it is, in fact, we can say that caprolactam, it become an amino acid if it get hydrolyzed. Now, the first question, how this caprolactam formed? This caprolactam formed, we can make this caprolactam directly from suppose phenol. Let phenol is there. On oxidation and heating with copper, first cyclohexanone will form. Cyclohexane means no double bond, non means ketone is there, and we know that C double bond O group combined with hydroxylamines, even the derivatives of ammonia, gives oximes. Oximes means the water get removed, and water means this H2O and this O. And these oximes are very useful in various fields, even medicines also formed. So, NOH. Oximes. The conversion of oximes into amides in presence of acid is Beckmann rearrangement. So, when it is treated with acid, that is H plus, the amide get formed. Amide means these 5, 1, 2, 3, 4, 5, no change. It means the 5 chain will remain as such, but at this carbon there is a rearrangement. Rearrangement means the O will be here and H. So, means C double bond O and then NH, this, and the chain of 5 carbon will remain as such 1, 2, 3, 4, 5 and then then this. So, this NH, CO and 1, 2, 3, 4, 5. So, this is the structure of caprolactam, and which can be prepared through this chemical change from phenol to this. We can form from benzene. Benzene, first we convert this benzene in alcohol and then this steps. And then polymerization of this caprolactam at this temperature and in an atmosphere, it provide the chain, it means it is a nylon 6. So, what will be the structure of nylon 6 if we polymerize this? The chain will break here and we get CO, CH2, how many 5 rings are the chain? 5 and then NH up to N. And why it is 6? Because the number of carbons are 6. Now, properties. Nylon cord, nylon ropes. So, this application we know. Now, the properties: high tensile strength, excellent chemical resistance, good mechanical strength and heat resistant, easy to process. At it, and one point is also there, it can be dyed easily. So, it is transparent, but we can make convert in any color. Application: toothbrush bristles, surgical sutures, strings of musical instruments, large variety of threads, ropes, filaments, nets, as well as hosieries, and 1/4 is it can be sterilized. So, we can write sterilized means it is basically used to form some medical instrument or vessels. Now, next is nylon 6/6. Nylon 6/6, nylon means a family member of polyamide. Polyamide means NH and CO is there. So, nylon 6/6 is formed by copolymerization of adipic acid and hexamethylene diamine. And why we take this adipic acid and hexamethylene diamine? Amine, because we required NHCO and this NH group will be get from this NH2. Now, NH2, CH2 and 2NH2 is required. Why 2? Because the functionality should be at least by 2, that is the monomer should be at least bifunctional. Now, how many number? Which number I write? Since it is nylon 6, 6 means the number of carbon should be 6. So, first 6 is this. So, what will be the formula structure of hexamethylene diamine? CH2 6 NH2 NH2. If you write 1 NH2, it means there will be one functionality, it means this will not be able to form polymer. So, we write di. So, bi. So, that is why hexamethylene diamine, diamine means 2-amine plus adipic acid. When we draw the structure of adipic acid, COOH, because we know that NH for NHCO acid group must be there. Now, since chain is there, I do not know what number I should be right there, and functionality 2 is mandatory. So, COOH. Now, second 6. So, number of carbon should be 6, 2 in acid. So, remaining 4 with chain. So, this is the formula of adipic acid. And when we draw the structure, then condensation polymerization will take place. Why condensation? Because something get liberate. So, COOH, OH and then H, same here and same here, because it is a long chain and more than thousands molecule get combined. So, NN. So, what will be the formula? The formula will be NH remaining this. Now, 6 CH2, 1, 2, 3, 4, 5, 6, you can write directly CH2 6, this, then NH, CO, then CH2 4, CO. So, this is the structure of nylon 6/6. And monomers, adipic acid and hexamethylene diamine. It is a family of plastic and its property includes moisture, it has significant effect, easy to process, it has very good tensile strength, it has mechanical property, good heat resistant or etc. We can write directly property of nylon 6 here. Application again here, it is used for making coats, ropes, some medical instruments because of good sterilization property. It can be dyed in any color, it can be used in carpet fibers, airbags, tires, ropes or etc. Now, next is Decron, ropes etc. So, in this lecture I finished the structure, properties and application of 5 polymer. The next last polymer, which is a Dacron, Terylene or polyethylene terephthalate. I will discuss this in next lecture, and okay, sorry. So, I finished this lecture here, and one polymer remains, which is a polyester, a member of fiber family. So, I will discuss this polyester in next lecture with conducting polymer. Thank you.